and welcome to this webinar today with Rapid Silicon and with myself from Aduvo. We're going to be taking a look today at some really interesting future of FPGA, particularly from a Rapid Silicon viewpoint. It's going to be really exciting. Just a few little housekeeping things as we move through first. If you've got any questions as we go through, please put them into the question and answer box. And we've got a team of people that will try and make sure that that we don't forget to answer those today. So first off, we're going to be having a great conversation today. We're going to be talking about the future of FPGAs and particularly how Rapid Silicon and their technology and its approach is helping create a new programmable revolution. I'd like to thank Rapid Silicon for hosting me and asking me to do this. And I want to introduce my good friend who I've known for many years, Jason from Rapid Silicon. He's going to give you a brief introduction, and then we'll take it from there.
All right, thanks, Adam, for the time, and welcome everybody to our webinar. Thanks for attending. Looks like looking through some of the names, I've already met many of you over my course of my career, which many of you may know. I was at Xilinx before this for 8.5 years, managing the cost-optimized portfolio and, of course, Zinc product lines. Of course, now I've moved over to Rapid Silicon. The trend, of course, existed in an industry where the large FPGA vendors were making a focused shift to data center type products, which we'll get into the presentation today. We find that there's a huge gap being exposed and a need for a new type of FPGA that fits a embedded intelligent edge market space, and that's our direct focus here. We'll kind of get into that a little bit too as the presentation goes on, but I've been in FPGAs my entire career. My first FPGA I ever programmed, and we'll do a little challenge here with Adam, but mine was a Xilinx 3096A, built an Ethernet MAC into an FPGA. And I did design engineering for over 10 years before going into technical sales, marketing, and then, of course, management. So that's my background there.
I think we could start off really. I think one of the things that's really interested me, I've been designing FPGAs for 22 years or so now, and I've seen a real interesting change in this. I'm sure we're going to touch on your points in a minute, Jason, as well. But I've seen that evolution of FPGAs when I first started, where we were using them for perhaps glue logic or to connect systems together or do a little bit of processing. And over the years, we've seen them evolve to become including more of the functionality, doing video processing, signal processing, handing off acceleration. And then we've seen that introduction of embedded processing. It actually started very early on in sort of 2004, 2005 times, but it wasn't, like all things on this journey, it wasn't that usable. It was there, it worked, but it wasn't as easy to use. And we've seen that evolution into the newer devices where it's a little bit easier to begin to use. And I've also seen significant sort of changes in applications that FPGAs have moved into. They started with sort of being used very much in the defense and the military and the aerospace type world, those very high-end sort of costly developments. And they've really moved, and I've noticed this in particular in the little consultancy we run. They've really moved into the edge and to consumer devices, and they've become very much more ubiquitous than they were. But obviously, I've seen this as a designer and working in different companies. You've sat, Jason, you've sat at a much higher level and had a much higher view over this. So I'd really be interested to get your take on this and where you think it's going.
Yeah, great. Yeah, fundamentally, and going back to our past and our history together, Adam, of course, one thing that you and I were both on the precipice of was when FPGA companies started to make the shift to become SoC companies, right? That's when there was certainly a need where you needed to integrate more embedded processing capability into the FPGA. Of course, the flexibility, the compute acceleration, the IO expansion, interface adaptation, hardware abstraction, all of those features were critical inside an FPGA still. But at that time, we're talking 15 years ago, 10, 15 years ago, everybody was still bolting the FPGA up to an embedded processor. And when we looked across the embedded space, right? Now, and across that embedded space, there were ARM Cortex-Ms, there was MIPS, and there was like your first low-level Cortex-A type processors that were being put onto a board discretely from the FPGA. So you had your two components, and customers complained that, of course, you had to build an interface to go between those. It required a lot of pins. It took architectural decisions and mapping and bandwidth calculations to make sure you had everything you need to make those two discrete devices work together. And that's where the light bulb went off. And we just saw then, 10, 15 years ago, this growth in the embedded edge and of course, trying to save customers cost and as well as design complexity, and then integrating these together. And that's where the birth of Zynq 7000 came out, which was the first SoC, really released to the market. And you and I, again, were at the inception point of that. I, of course, at that time was working for a distributor and I created the first board for that, Z board, which was very popular board. And then, of course, created the introduction training material for that board to get the hardware going, the software tools going, because it was a very difficult process at that point in time at the beginning. It was a rough start to get that going. But then, of course, you took it to the next level with your Micro Z Chronicles. So that's where we both came into the, together and helped bring that product to market. But here's the key, is that since then, there has been no looking back. That product has been an incredible product for Xilinx and for our Intel and the Cyclone 5 SoCs of the world like that. But those are great products. But here's the problem, is that they're great products. Customers ask for those products. They want more products like that, and they want a roadmap for those products. And of course, no company like that, nobody has an SoC roadmap product in their portfolio. Nobody. Zynq 7000 now is at the point where it's reaching, well past the midpoint of its lifespan. It's lacking security features. It's lacking, DDR memory interface topology and technique. It's missing some of the key things. It's missing I/O capability for higher speed I/O interfaces and interfaces like MIPI. So there's just lots of holes in that platform. But yes, this evolution that we've got here was an amazing evolution. It was a revolution itself to bring the SoCs to embedded processing to FPGAs to create the SoC. But it stalled there, and it needs to move forward for that embedded intelligent edge space.
Oh, that's really interesting. And it's like you say, it's been a long journey. We've known each other for a long time. We've been on that precipice, and we've seen it come through. And it's crazy to think it's 2022 and we've been working at it for such a long time. So I'd like to say, where do you see that there's a lot of opportunities and things there in the FPGA space? So what do you see that opportunities and gaps really are that we can take a look at?
Great. I mean, it's a great question. This is really where we see, the explosive growth in technology. One of the great things about FPGAs is whenever there is an emerging technology, FPGAs seem to be deployed at the forefront of those emerging technologies, because it takes time for customers to develop an ASIC for their end product, if even that is an applicable solution, or it takes time to develop the technologies to solve those problems, and you need a flexible environment for that. So FPGAs are always on the emerging edge of technology, and you can see in these markets here, we are definitely there. We're seeing the evolution of the smart cities and surveillance. It's kind of an interesting question in smart city and surveillance, and this is a one for you, Adam. What country in the world leads for surveillance in smart cities?
So I'm going to say with the UK. I think we've got
Yes.
I think we've got one of the most numbers of sort of smart cameras and CCTV cameras in the world.
I think the default answer, most people would say it's China or somewhere, but yes, it is the UK. That is correct. And a lot of the customers there are deploying kind of embedded SoC technology into those cameras for a number of reasons, which we can get into. But that's just one, right? And this is not going to slow down. This is going to increase. we'll go through all these, but our automated smart factories, right? There's more intelligence going to smart factories to increase automation, to increase defect, yield rates, right? Things like that. Intelligent networks. We can't simply, with all of our phones and iPads and computers and all of these cameras that are being deployed in cars and cities, can't just simply push all that bandwidth into the network, right? We have to do some smart, intelligent filtering at the edge. So we're just not flooding the network with expensive, data that's going back and forth. So you can keep going on through the list. The audiovisual broadcast systems keep evolving. Autonomous vehicles, we're seeing, just not only for driver assistance, but for safety, for increased vision, things like that. Remote medical, all of these fields. That's all technology does, is it keeps evolving and emerging. And this is a real key point that I want to address with rapid silicon, and why we're called rapid silicon in some ways. You simply can't release a product family every 8 years, which seemed to be the cadence of the bigger companies, right? It's expensive to keep rolling out one product family in architecture, then another big product family in architecture, and another big product family in architecture. All of these markets we're talking about here, they don't need a data center focused product. They can't afford to put $1,000 FPGA into a smart city camera or an autonomous vehicle camera, right? Or on the edge of every single network or NIC card. You can't put that there. You need low cost, but compute intensive or compute capable devices, SoC type devices in each of these spaces. So when you have a company like the big guys that we've talked about, and they keep building a span of products that reach from the low end of the mid-range to the high end, it's very difficult, especially as those high-end parts just get more and more complex, require more and more engineering resources. And those are incredible parts they're building. And they're going to solve very incredible tasks up in the cloud and the networks. And there's certainly a lot of money up there to go chase to do that. But you need somebody who has a focus to go build products for these types of markets, because there are a lot of applications here that are FPGAs that are a perfect fit for.
That's a really interesting point, and that edge processing is quite important because the volume of data and the variety of data that's being produced it's just phenomenal. Like you say, there's no way you can send it back to the cloud, back through the data centers, the networks, even with like 5G and future generations of that. There's just no way the networks can handle that. So this leads me to one of the interesting things. So we've talked about a little bit about like the journey that FPGAs have been on. We've talked about the applications, the challenges that they face. One thing that's kind of close to my heart at the moment really is that as these devices change and evolve, we've not really changed and evolved how we design these devices. We're still kind of designing these devices like it's a little bit like the 1990s, and there's some architectural things that we could do there. But there's also some other interesting elements there in the the engineering community. I think one of the things that's come about over the last sort of maybe 10, 12 years has been a really good community of people around the FPGA, across the world on the web. They're passionate about it. They want to see it. They work with all sorts of technology, and that leads to sort of demands for open source, which I know is really at the key and the heart of sort of rapid silicon. So I'd really like you to sort of give us a little bit of an introduction to, Rapid Silicon, who they are, because we've talked about them briefly, but, who they are, what makes you different to the rest of them, and how that sort of open source and everything fits within what you see going forward for them.
Great. Yeah, I mean, fundamentally, Rapid Silicon, we're coming at this from a little bit different perspective than your traditional FPGA company. We've seen some other upstart FPGA companies, and they follow the same blueprint that the big two have started 35 years ago, right? Let's just copy what they've done and follow their same model. We are breaking that trend. So yes, you hit on the fact that we've just seen a trend. We could spend an entire discussion on open source. We can talk about what open source has done to industry, right? We can look at what open source has done for the operating system, right? You could talk about what's done for the operating system. Linux 20 years ago was a concept, and now it's the #1 deployed embedded system.
Who uses?
Yes.
I was going to say, who uses, you said this to me the other day, who uses Borland compilers anymore because of GCC?
Right. Well,
You know,
yeah,
it's had
exactly. That was good.
such a
Yeah.
change.
Yeah, compilers. Nobody uses Borland and Microsoft compilers anymore, right? And look what RISC-V has done for the instruction set architecture. Nobody was challenging ARM or MIPS or any of the other big embedded processing companies, and of course, RISC-V disrupted that entire ecosystem. And Sci-Fi is the company that really commercialized and productized that and grew to a massive company. And it's an interesting note, the CEO of Sci-Fi, who grew that company, who had that real ambition to promote the open source instruction set architecture and challenge the big players, is our CEO here at Rapid Silicon. So his name is Dr. Vidya Shavani, and he has been an incredible proponent of open source. So, but when you look at open source when it comes to just what it's done for operating systems, instruction sets, C compilers, but also its AI deployment, all the frameworks for that are open source, right? You look at robot operating systems, video encoding streams for like GStream, a lot of these ecosystems are open source. And technology is shifting over to a open source ecosystem architecture. That's where the evolution happens. That's where customers and people are expecting. So it has to be into our DNA. So open source, as you'll see, is very much at the heart of our DNA, not only how we build our products, but how we implement our design tools. And we'll get to that in a moment. But the other key things I'll reiterate on again, is that as we showed you in that slide for the embedded edge, the intelligent embedded edge, we have an incredible focus just on the intelligent embedded edge. That's where we want to build products. We want to build products with a consistent architecture, our consistent roadmap. And our architecture, which we kind of term nimble engineering, is what enables that consistent architecture and roadmap evolution. So, and then the final thing is that we, again, believers in open source, have a belief in reinvesting into that ecosystem, right? We want to keep giving back to those ecosystems, contributing to that ecosystems, and really spawning that kind of creativity and innovation in those places.
That's an excellent, I think that's an excellent example.
Yeah,
you know, it's an excellent, it shows a passion for sort of the edge and the technology and where you go from there, and that ecosystem thing, it really resonates with me, because I like, you know, the one thing I've learned over the last few years is, you know, we all go a lot further if we go together than
right.
we do sort of than we do if we sort of trying to one up on each other and such. But you just mentioned on sort of you did touch a little bit on open source, and like you say, we could probably fill hours or 2 hours talking about what you're doing for it. But can you just give us a little bit of an example as to just how, just because it's been a thing that we've talked about for a long time in the FPGA world, you know, open source, and it's never quite there. So can you just give us a little example of what you're doing with to support that community?
Yeah, I mean, like I said, it's at the heart of our DNA is open source. The first thing that we kind of challenged ourselves with at Rapid Silicon is, can we build a completely open source EDA tool flow? And we have, that was the first task we went after. And of course, we codenamed this Raptor as our tool flow. And we started looking at all the components of what it takes to design an FPGA or an SoC system, right? Of course, everybody has some kind of cockpit for IDE for design entry. Everybody has to do IP management, right? You know, how do you get IP in and out of your system? How do you manage your own IP in and out of the system? Of course, there's the common components of synthesis, place and route, timing analysis, and of course, simulation. And then finally, with all these open source frameworks, like for AI and ML, you need to have an integration flow for that as well. So these are the key components that are in any EDA tool flow. And of course, we had to look through the ecosystem and say, are there open source components that can plug in here? And we did a very exhaustive analysis of each of the tools that kind of fit each of these components. At the end of the day, we selected a group of these open source components, and of course, we had to make them work together, right? So we had to build a unified database underneath of them all, so they can all interoperate together. And then, of course, we evaluated the quality of each of these open source component tools to see if they are of a commercial level. And what we found is that quite a few of them are, like OpenSTA, for example, is already used by AMD, Xilinx, and Microsemi. There's other tools out there like VPR that have been in the academia world, funded by large players, corporations and made large investments into it. But this has been living in the academia world, being worked on by PhD students and around the world. And of course, this is led by a professor who used to work at Altera, and he was kind of the architect of their place and route tools there. So there are incredible pieces to this out there that nobody's really using towards a commercial product. And there's others like Yosis for synthesis, which we felt was a very good tool, but of course there was room for improvement. We can do more and work with them to improve the tool. And I can kind of show you some of the results of what our combined efforts there are doing. So at the end of the day, our analysis and assessment was, yes, we do believe we can build a complete open source tool flow. In fact, at the very beginning of Rapid Silicon time, when we were rolling out this, we had a two-pronged strategy. Let's work on an open source tool flow. Well, let's give you a commercial third-party tool, that you could use at the same time, just to help accelerate those early customers. But we've made so much progress so quickly with these open source tools. And this is just a testament, again, like you said, power numbers, working together as a community. When we started telling these communities that we are building a commercial silicon target to run these open source tools on, they got incredibly excited. And of course, we've seen other commitments from other industries to support this. We've put financial commitment, we've put our engineering, many of our own engineering resources into this. And now I believe what we have is a pretty incredible tool. And like you're saying, it's impossible, I think, you'd be closed-minded today to start a company without some kind of open source, characteristic to your company, right? There's just so many reasons why. I mean, the community engagement, as we've already seen, right? Access to the tools, support increases, endless and continuous innovation and improvement, right? No more end-of-lifing tools. Like if you're familiar with using like the old Spartan 6 tools, that's a catastrophe, right? That would never happen in an open source tool. It enables, customers, us to go focus on differentiation and optimization towards our architecture, right? And the proprietariness of it is just gone, right? We've already seen, again, incredible investments into this from big players, big corporations. So this is a train that will not stop and just keep continuing to gain momentum. But the other thing the open source tools do, and I've had so many customers come to me at my previous company and ask me, I'm building this really complex IP. Your tools aren't synthesizing it, I know, as well as this other tool or this other tool. Why not? And of course, they're never going to, those tools teams are never going to go modify their code just for one customer. But this, having access to the code, would allow that customer now to go modify it for themselves and make those kinds of mods and have their own differentiation that gives them a better end product, right? So at the end of the day, we are on a path to release the first commercial grade open source EDA tool. And in fact, one of the things we want to do in the webinar today is announce that we actually have our first alpha version of this tool, our Raptor tool, available for customers now. And it's our alpha version. It gives you a basic flow through the tool so you can see what it does. It has first initial look to our IP integration tool, which is an open source based tool as well called LiteX. And of course, it will be a great tool for doing some RTL analysis. So if you want to take your piece of IP and see how it synthesizes in our tool, and get a relationship between resource counts and utilization, that's what it's capable of doing right now. And we are releasing a new updated version of this tool every quarter moving forward. So in December, I'll have our beta version. In March, April, or February, March, I'll have our pre-production version of the tool. So it's constantly and quickly evolving.
That's fun. That's fantastic. And I had a sneak peek of Raptor a few weeks ago, and I've actually wrote some blogs on it, and it really does work. It has a really nice and simple feel to it, and really small download size as well, which was quite nice.
Right.
So
Nobody wants a 20 gigabyte or 60 gigabyte download that takes half a day to install, right? That just doesn't make any sense.
it's crazy, isn't it? But so we've talked a little bit about the tools, so and you've given a little bit of a hint about sort of the the devices and what they can be used at the edge. But can you give us a little bit more of a deeper dive, really, on what your product portfolio is? Because you've got some really interesting uh, differentiations, I think, in there. So can you give us a wander through that?
Yeah, well, actually, before even jumping into that, I want to just go and say one more thing about the tools,
Please.
and that is the we've taken the tool, like you've done an evaluation of it. We've done more with the tool. We've taken it and just given it to other third-party companies that do an analysis of the tools themselves, right? They'll do their own deep dive analysis and actually simulate it versus other tools and do a comparison. So one such company we gave that to was a Swiss company called the EPFL. And this is all they do. They simply evaluate EDA tools to evaluate synthesis, packing, and efficiency of design effectively. Well, we took that pilot version of our tool, which we released in July, so the previous quarter, gave it to them, and they have a design suite of 40-ish some designs that are very complex, very hard to synthesize. And in doing so, we actually won 24 of those contests. That's twice more than any other winner, beating out the typical winners. And this is really based on an improvement we've made to the Yosis synthesis engine, adding a design exploration algorithm to it, which is using a sense of artificial intelligence, an AI algorithm for synthesis packing, which again, nobody's really done that before. It's one of the ways we're bringing innovation to this and try to improve these tools. So our goal with Raptor is not to come out with just an open source tool that most people might have the idea that is a low quality tool because it's open source. No, our goal is to bring a commercial quality open source tool that competes with the Vivatos, Cortices, and other tools of the world, right? We want to have a tool that does that. And I will just want to say this too, well, maybe we'll get to that later. We're able to do this because we have hired some of the best EDA tool engineers in the world. We've got them from, of course, Altera and from Xilinx and from the industry, from Synopsys. We've got some of the key people we felt were the best people in the world and brought them together to build this tool. So it's not surprising to me that they have incredible results like this out of the gate.
That's fantastic. That's the first time I've seen that. That's really quite fantastic performance, to be honest.
Yeah, I mean, and like I said, we've taken it to one step level. Of course, we do our own designs. We have a design suite inside our company now where we do this kind of analysis too, against the over 170 designs. And of course, our goal is to be the best, have the best synthesis tool out there. And we know our place and route tool is very capable as well. So we get, each of these steps we keep putting together and improving, it's just going to put out a very incredible tool. And our goal here, like you see in this chart, is our comparison to the nearest competitor, not just one company, but the nearest competitor. And this team won't be satisfied until they've gotten, the best results across the board in this design suite. And this is pretty much the industry design suite that most companies use.
That's fantastic. That's really cool. So let's
Well, you were asking
talk
about
about
the hardware, right? So
yeah. So let's see how this works on this. So let's see a little bit about the hardware. And I only say that because I've just noticed we've got a question where somebody just asked a question about what FPGA does this tool support. So I think it's time to sort of introduce the Rapid Silicon
yeah,
FPGA.
that's a great question. Yeah, because we haven't talked about that. Fundamentally, at the end of the day, when these open source tools, when we bring them to the commercial level, there's nothing stopping you or anybody from targeting any FPGA. They'll just have to build the plugin compiler for their own architecture, right? And fundamentally, that's what we're doing. We're bringing these tools to the open source tools to a commercial level. And then, of course, we're building the compiler that targets our architecture, and that compiler is optimized to our architecture. It's no different than like your GCC tools. You would target an ARM Cortex A9 or whatever, or a RISC-V under the hood. They're just build options, and that enables a different, optimized compiler for that architecture. So yeah, our goal here, again, with open source being in our DNA, we are building, of course, silicon devices as well. This is this is the whole goal of the company, is to build intelligent embedded edge products for this these markets. And in our evaluation of looking at logic architectures, of course, an FPGA is a sea of lookup tables, flip-flops, block RAMs, and PLLs, and DSP blocks, and multipliers, accumulators, all that, right? But the logic block itself, the lookup table, the flip-flop, that architecture itself, the routing between them all, there's a bunch of varieties of those that exist today in the market, from Intel and Xilinx and Microchip, Efinix, all these other guys out there, right? That said, there again, in the academia world, there was an open FPGA architecture that was gaining momentum, again, being optimized and worked on by PhD students around the world. Nobody had really taken that to the next level commercial step until now. And of course, we have taken that open FPGA architecture, which is a modern architecture, something like you might see in a modern FPGA like a Xilinx or Altera, not something you would see in an older architecture FPGA like you see from Lattice, Microchip, all the others out there, which is still an old 4-input LUT. Now the world has really moved on to a 6+ input LUT architecture. All the synthesis algorithms and design studies have all shown that. So we took that open FPGA architecture and actually built a prototype chip, which we called our Genesis prototype chip. We built this earlier this year. We received this chip back in May, and actually this right here is a physical, real picture of our chip. We got this back in May and had this chip running in 3 hours. And that was with the Raptor tool building the code for this. So we had a fully functioning EDA tool and a fully functioning opening FPGA architecture in just a few hours. So that's pretty amazing. So that's the first product differentiation step. So we have open source in our tools, and we have open source in our DNA for our architecture as well. The next thing is with an FPGA, of course, or an SoC. Again, our focus is to build SoC products, not just FPGAs. That's the evolution we're continuing. But in an SoC device, you need things like high-speed SerDes, you need external memory interfaces, and of course, you need embedded processing, whether it's RISC-V or ARM, and you need a very flexible I/O capability, right? So these are major components that every SoC needs. Now, as a newer company, we can design all of these components ourselves, but it would take us a long time to get there. And there's no point to reinvent that wheel when the ecosystem and the industry already has a vast catalog of these IP blocks that you can simply just buy and bring in. And it, of course, it gives us the flexibility to evaluate who the best SerDes manufacturer is for our device, who makes the best memory controller for our device, and which of the processing companies gives us the best fit for our companies, right? In the bigger companies, you have to design one of these blocks, like the SerDes, and try and make it work on all of your products. Sometimes that gives you maybe really good performance at a cost of higher power and cost. Something like that. We can now fine tune this to exactly what we need for this product. And so that is our goal here, and product strategy is to leverage industry standard and, most importantly, silicon proven third-party IP. And again, what I mean by silicon proven, we looked at vendors had already used their IP had already been taped out in many chips, especially at the technology nodes that we are looking at. So there's history, therefore known reliability, right? And improves our time to market. That is the second real pillar of our architecture. The third one is, and this is something nobody's doing in the low to mid range, is we've introduced a network on chip on our device. Now, if you look at a data center class product product from the big two, you'll see in those devices there is a NOC built into those chips, but not necessarily in their low to mid-range devices. We have a fully integrated NOC inside this architecture, and this has a lot of value. One, the first number one value is for the NOC. It eliminates you using the expensive FPGA routing resources to move data between these hardened IP interfaces like SerDes to DDR. If you were bringing SerDes data in a traditional FPGA, you have to push that through all your expensive FPGA routing to get into your DDR interface, and from your DDR interface back to your processor. So that is a very costly proposition. And of course, the NOC resolves this and gives you, of course, deterministic bandwidth, which of course FPGA fabric we know does not. So this is an architecture that is evolving and will be in every FPGA. It's in basically, if you look at any ASSP from your common ASSP vendors, they all have NOCs in them now. It's a late comer to the FPGA world, but it's inevitable. And we are the first ones putting it into this low to mid-range device. The other real benefit of the NOC is all of our IP can plug into that NOC. So now doing device assembly and device integration is very simple. And this is a key thing. This is how we will build a consistent roadmap of new products moving forward and develop variants quickly because of this architectural decision. We are architecting the device to be flexible, to add and move components and grow and shrink devices to meet power and cost of certain market demands. And of course, you can't do any of this unless you have a dedicated focus on building edge products with no data center distraction. We are not in business to build data center parts. So that is at our core, our kind of guiding principle of our hardware. And what
Excellent.
Yeah, and what that manifests into is what we call our Gemini, our first product, which we call Gemini. You know, and I will say this: all of our devices, we're targeting 16 nanometer TSMC. So everybody asks, what fab are you using? What technology node? 16 nanometer TSMC. We've done all the evaluation against different fabs, against different technology nodes, but 16 nanometer TSMC gives us our best performance per watt per cost, right? It's the best sweet spot for that node. But more importantly, it gives us the best lifespan and supply chain stability. We know TSMC at 16 nanometer is increasing capacity on that node over the next 2 years. So that is fundamentally where all of these products are being built on. The Gemini, we call it the new standard for the cost-effective embedded FPGA. Again, here we go, intelligent embedded devices. We're targeting somewhere between 50 and 100,000 logic cells for this device. And again, it's the open standard 6-input LUT in the fabric, just like you would see with any modern FPGA. There's block RAM, there's DSP blocks. We are hardening a 32-bit RISC-V processor because, as we've talked about, Adam, many times, this is where what Zinc was the game changer for this and brought the embedded processing into the space. Even customers who were using just generic FPGAs, over half of them, if not more, were integrating a soft processor in the fabric anyway, which makes sense. So now we just give you a very robust 533 megahertz processor, which has, of course, MMU and MPUs for Linux and RTOS support. There's localized memory here for that processor. And we've hardened a memory controller. We're going, there's a generation where we hardened memory controllers and devices. Then we went to the next generation and took them out. And we, of course, are putting them in because it's just, you need this to get the performance capability to support modern memory interfaces like LPDDR4 and DDR4. And in this memory interface, you also get a memory, on-chip memory of 256 KB for code storage here, or data buffering, or whatever else. But at the heart of the device, you do see the NOC. That's what integrates everything together. There's a general connectivity block with some common interfaces like USB and gigabit Ethernet. Security and boot all is done in this hardened block as well. And finally, as vendors have shrunk technology nodes and gone to smaller geometries, there's been a sacrifice that's been made, and it's been IO density. That's what's been given up as we've shrunk to smaller technology nodes. We have invented and architected with a third party who has expertise to build an IO block that's optimized for this node and for our interfaces, and returns that IO density back. So even on our smaller devices, we have an incredible amount of IO density. For that is one of the major applications of FPGAs is IO expansion. So this is our first part we go to market with, and I believe this fits kind of where if I would have built the next generation lower cost embedded intelligent type of SoC at my previous company, this is what I would have targeted to go build. Now, of course, there are going to be applications where you need more processing power, like 64-bit compute processing power. And what you may notice, there's no gigabit transceivers on here for high-speed interfaces. That's where our second product, which we're kind of co-designing these products together in parallel, because what you notice here at the heart of this Orion product is a memory subsystem with RISC-V, FlexNoC, general connectivity, FPGA. It is the Gemini product. This is where nimble engineering comes into play. It enables us to build derivatives quickly. Now for Orion, you get the dual ARM A53s, so 64-bit processing or 1.6 gigahertz. And of course, increased logic density. So we're talking somewhere between 100 and 350,000 logic cells. We'll have a portfolio plan in here. And of course, we're adding gigabit transceivers in here as well. 16 gigabit transceivers with hardened multi-protocol PCS blocks to support standards, because when you get to these higher data rates, you need to have a hardened interface PCS block to interface them. Of course, native blocks for PCI Express Gen 1, 2, 3, and 4, and Ethernet. So they're really, with Orion, there is no product in the market that will have this kind of logic range density with this many transceivers and PCI Gen 4 support. So again, we are building devices to support the next generation edge type of devices, not the last generation, but the next generation, this generation and the next. And of course, the memory controller goes up to higher bandwidth and increases its memory density as there as well. So a great question came in, MIPI cores. I went over this very quickly, but you'll notice that we've got two different types of I/O banks inside the device, a high performance bank and a high voltage bank. The high voltage bank is really a 3.3 volt bank. And I will go back here. If you see in our Gemini, they're drawn asymmetrically because there's more 3.3 volt IO in Gemini than high performance IO. Whereas in Orion, there's a better balance. There's almost an even balance of these two in the device. The high performance bank gives you high speed interface connectivity to interfaces like LVDS, as well as MIPI. So our IO banks, the high performance IO banks, will natively support this. And we are building gearboxes on the back end for those, in those IO blocks for those high speed interfaces to bring them down to fabric speeds, right? So Gemini, our target is to support 1.5 gigabit per second MIPI natively in the high performance banks. And in Orion, we want to support it 2.5 gigabit per second MIPI interfaces on those banks. So great question there.
That's a good question.
Yeah, and then, like I said, last thing I'll say about the hardware architecture, again, this is what we call nimble engineering. You know, there's your Gemini product, the first one I showed you. Orion bolts on the transceivers, the ARM processors. That gives us a, very, complete IP ecosystem to build parts, right? We have the reusable SoC and IO blocks. We have a scalable fabric architecture. And we have, of course, the ability then now to go build cost-reduced variants where we can reduce or remove or change the number of processors or add, reduce, or remove the number of transceivers. So if a market dictates, to hit a certain price and power point, we need, only 4 transceivers, only one 64-bit processor. It's a derivative that we can make very quickly and easily. And that is our goal, is to, and another thing about this architecture, can we support, other IP? We've already talked to 2 different customers that want to integrate their own IP into this device to provide new networking interfaces, right, for industrial protocols. And then others to talk about image signal processing blocks for bringing in very complex video data and then processing it quickly in the hardened block there. Those are all options that this architecture enables.
So I have a question on this architecture then as we're talking through, which is really something we've talked about in the past, but I think the attendees will find it quite useful. Is so I think this is the first device I've seen where you've got both a RISC-V and an ARM core. So why sort of the two different ecosystems? Why not sort of a standardized on one or the other? And I get the flexibility, you can do derivatives, but I'm quite interested in that.
Great question. And I'm going to say two things about this question. One is first our open source nature, right? That we have the open FPGA, we got the open source ISA RISC-V, we got the open source EDA tool flow. What nobody really caught me on with the tool flow is there's one component in the EDA tool flow that we can't quite open source. So there's one proprietary component in there, and that's Verific. That's what parses your RTL, your VHDL, your system Verilog, your VHDL or Verilog into our RTL that we can synthesize, right? That's because this is not an easy task to do, and Verific does it better than anybody else.
Everybody uses Verific,
and everybody uses it. So
it's everywhere.
Until there's an open source version of this, or Verific releases some of it to open source, this will be the proprietary piece of this. But the reason why I brought that story up is because that gets us back to the reasons why we did two different processing technologies. Now, we assessed the market, and a 32-bit RISC-V ecosystem is very strong, very capable. Operating system support, driver support, everything is there, I think, at 32-bit. And that's where, of course, RISC-V started, right? So it's more mature and had time to develop that ecosystem. We feel like right now, at 64-bit level, RISC-V is not quite as mature as ARM is. So that is where the decision was made to put an ARM processor for 64-bit level. Plus, the ecosystem is very rich already with customers already who are familiar with the ARM A53. So the familiarity with that processor is the most popular processor, I think, developed from ARM to date. And so customers who come from an ASSP or another PLD vendor, of course, will have that familiarity, know what to expect out of this device. So again, there's nothing to say that in the future, as 64-bit RISC-V evolves, that we can't turn a derivative out like that, right? Where we have 8 cores and maybe they're more focused on something else, or even just 1 core. But yes, at the time, and maybe you can add some insight to that from your experience, because you work with many customers too, but that's what we saw.
No, I think I agree with that. I think, we see a lot of 32-bit RISC cores. RISC-V cores we tend to put in very small devices and applications, where you just want that little bit of control. But the more higher application stuff seems to go on the A53 type, type processor core. So I think that's a fantastic decision and a really good explanation. And you've got some flexibility. I'm conscious of time, but and we've talked a little bit about the tool flow and everything like that. The NOC is something that I find interesting. We've said that that's the first time that you've put one into this class of device. It really does allow you to do, like you say, it really does allow you to scale and be flexible and have those derivatives. I guess as well, there's some benefits for there's some benefits for the designers in the logic in terms of determining, guaranteed bandwidth and such like, easier time enclosure and such like. Is that something you see, that the benefits are just not only for rapid silicon and that scalability, but also for the users and the developers?
It's a great question, and it actually ties into one of the Q&A questions we got. The NOC itself, the two values of the NOC are, it eliminates routing congestion, right? And it enables device variant building, because our architecture now is like a Lego block. All these pieces plug into the NOC, right? Because the NOC supports. And by the way, we are integrating a Flex NOC brand NOC. You could look it up. It's one that's been used in many SoCs across the industry, and it has a variety of support for AXI type of interfaces, open core, peripheral interface buses, and even others. There's a list of there on their site of what the NOC technically supports. But realistically, it eliminates routing congestion because you've now built a dedicated data highway inside your chip. That means we can do less metal routing layers, right, in our device. It means we can actually shrink the device. And this gets down to a cost question that came up. When I was managing those products at my previous company, especially the 16 nanometer class of products, they were very capable and quality products. However, they didn't scale down in price very well. That's where there was a gap between Zinc 7000 and Zinc UltraScale Plus. You had an increase in performance and there was an increased value, so there was an increased cost. But that didn't leave a home for those Zinc 7000 customers who need to migrate forward to a new generation. There was nobody fitting that price point. Our devices are built to fit that price point. The architecture itself is built to be optimized for power, architecture, and size that reduces cost. So I think you'll find when you, if you are interested in targeting our devices and we start quoting you pricing, you'll be quite surprised at what our pricing comes back into relative to the big guys. And it really comes down to our architectural decisions we made. But the NOC gives you, again, to get to your point, Adam, does much more than this. You have quality of service capability, there's memory protection, memory scheduling. There's, this gives you, when you have that kind of scheduling and protection on your data highway, that gives you increased functional safety resilience, right? There's a lot of value to the NOC, and I can go on and on about this, but at a high level, this architectural decision does provide quite a bit of capability.
That's really impressive. Really quite interesting. It's really quite interesting, to get that. Obviously, as more of a user than a sort of developer of those FPGAs. It's interesting to get the trade-offs and the decisions and the PowerPoint and the decision points that come through. So I guess we're quickly sort of coming towards the end of the hour. So I'm gonna ask you sort of a couple of questions that we've got coming up. So I guess, so what's next for Rapid Silicon? What does the next 12 months or so look like in terms of getting this out there to everybody?
What's next? No, that's a great question. I mean, I think, we are real busy rolling out these products. As I mentioned, the first alpha version release of our tool, we had a deadline to get that out by October, which was last month, and we did. So there is an early version access of that tool if people are interested in using it or evaluating it. We have a cadence of rolling again, another one out in December, another one out in February, March, and then another one in the summer, which will be our production class tool. And of course, our silicon, we expect that Gemini product to be available in silicon through eval kits and engineering samples somewhere in the second quarter of next year. So what's next is, of course, we're just busy trying to get out our products in general, right? And we will. And again, Orion is being developed in hybrid because it's got the same base architecture. Orion will follow a quarter or two after Gemini. So we're really talking in about the next 6 to 12 months here. In 12 months, I will have, of course, I think the Gemini product in complete production, and I'll have Orion in early pre-production availability, all within the next 12 months. And I think even Gemini, like the first silicon here, could be here as early as 5 to 6 months from now. So the goal is to get our tools out first so that customers can start evaluating and doing design porting or design analysis and evaluation on our tool, so that by the time silicon comes, they can hit the ground running, right? That's our kind of our goal there. And then, of course, we are talking to customers all the time about, they love, all the feedback we've gotten about the portfolio is it meets what they need from many customers. And then, of course, there have been a few customers that says, yeah, how about, and a question came in, how about giving me a GPU? How about giving me a video encoder? How about giving me an industrial networking interface on this? Of course, once we finish our tape out of Orion, the game is open, right? The world is open. We are not a company that's going to go build products and say, here, general product, and just say, everybody use this. We are listening to customers. So this is a customer-driven company When customers tell us, enough customers tell me I need a certain interface or I need a different combination of your IP, we will look at that in engineering and try and take that part out. Our goal is to release a new product every 6 months that meets specific market needs. Not once every 8 years, like you saw us like Spartan and Cyclone. Every 6 months we'll keep evolving this product.
That's quite exciting. So I'm looking forward then to receiving my my development board around sort of Q2 next year. Then sort of March, April time. It'll be.
You will get one.
I'll be able to put it on my desk and play with it. So I was going to ask the next.
Anybody who wants one will get one. So we will make them available.
So I guess we've got a lot of there's a lot of potential people interested in this. So what are the next steps? If you like you say, if you want to get hold of the tool chain, or they want to sort of register interest in a board, or they just want to talk to you about, hey, could we do a derivative like this for your next? What are the next steps? How do they engage with you and sort of take it from there?
The first thing is we do have our YouTube channel, which it's just YouTube and search Rapid Silicon. You can see demos of our test chip that we did. These videos are from the May or June timeframe. You can kind of see our open source tool strategy, what we're going, even a YouTube video demo of the EDA Raptor tool if you want. And of course, a message from our CEO to kind of give you that kind of, really set the direction of what we're doing. Like you said, what next is very important, but what we have done is very important too. We've taped out that test chip. We've got our contracts with TSMC. We've released the EDA tool. So there's a lot of things we've done. I can't really say more than the fact that we've done this and have moved at the rate we've moved at because of our experienced team. If you go to LinkedIn and look at our company, you'll see our executive staff has over 250 years of combined PLD experience, right? So we have, I think, the right pieces to move forward. But yeah, next steps, like customers, if you want to, anybody here wants to learn more about the product, of course, we have our product brief on our website, and I encourage you to go there. But we have created what we call our Early Access Champions Lounge. And there's updates on product development. There's access to the tools. There's access to documentation as well. So technical docs, our data sheet is online. We have our power estimator coming up here real soon. And about every 2 weeks, we have a cadence of new documentation going into this lounge. But yeah, that's where you get tool access. And of course, anybody in this Champions Lounge will get early access to silicon and eval kits, as you mentioned. So yeah, we have signed sales reps in Europe. That's Prisma sales. And we have signed sales reps in the APAC region. That's Braymac sales. So Braymac in Australia, New Zealand, and the ANZ region. Prisma for Europe, and for North America, we are in process of signing a few sales reps now. So we'll have increased sales coverage and direct localized sales support. Of course, customers who join the Early Access Tech Lounge here for us to Champions Lounge will also get the ability to have direct technical support. We already have a support forum our channel set up where you can fill out a form and with your questions or issues and hit submit, and you get an answer back. So we are moving very quickly, and there's again, anybody who wants to get started and evaluate this some more, of course, you can contact us and through our website, LinkedIn, any way you want, or through our sales channels.
Excellent. So there's a multitude of ways they can talk and engage with us. So we literally have a couple of minutes left. So if anybody's got any questions that they've not answered, that they've not asked yet, please ask them. There's one last question in there about UCI, which is the Universal Chiplet Interconnect Express, I believe.
Yeah.
Which I don't know if you have that or considered that on your roadmaps, Jason. I guess the flexibility would allow something, but.
So chiplets are definitely a strategy we're looking at. Now, first, it's probably our second generation type of strategy we're looking at. We are already talking to customers asking us about UCI. Because a lot of customers now, we do see a market as devices are shrinking and things are miniaturizing, the need to build the chiplets. And so a chiplet strategy is definitely in our portfolio. That is the type of kind of custom IP interface that we can build into this device that gives it through AXI to UCI on one side, right? Now you can talk to external chips. So that is a roadmap item that we are investigating. But yes, we have significant customers asking us about that as well.
I thought you might. So like, let's say if anybody's got any questions, just feel free to ask to pop it in there. But I guess if not, then thank you very much to everybody for attending and listening for the last hour. I've had great fun. I've certainly learned a lot. It's been great as always chatting with Jason. I presume we'll be. Oh, there's a question just popped in about where we will be manufacturing. Where will be manufacturing be based out of?
Great question. Yeah, so we have signed TSMC already. We have and we've also signed a third-party operation quality and operations company as well, because to do that ourselves, it takes time to get the certifications on. This company's already done it. They already do third-party services for other major chip suppliers and vendors out there, so they've got all the processing control. But we are based in Silicon Valley. We have a couple worldwide design centers, and we're adding a couple more as we go. But yes, we and like I said, we're TSMC is the fab. Silicon Valley headquarters is hopefully that answers that question.
Oh, I think it.
Yep.
I think it does. So as we get to the top of the hour, I guess we'd better thank everybody for attending, and then we can we'll wrap up. I'm sure the video will be available on replay on demand on your YouTube channel if people want to watch it in a little while. And yeah, Jason, it's been fantastic chatting with you again and learning about your tools, your offerings, your journey. It's really quite inspirational and exciting. And yeah, I'm sure people will be wrapping up. If there's anything you want to say just before we finish.
No, this is great. I mean, this is thanks for your time, Adam. Thanks everybody for joining. This had some great questions, and I hope everybody's excited about this as I am, because it's nobody's taken on that challenge to do open source tools. Nobody's taken on that challenge to build kind of this next generation embedded SoC architecture. We see some from our competitors. Yeah, they're building another new FPGA, but it's still the old architecture. And a lot of them don't even integrate processing yet. We just saw, like we described with Zynq and Zynq Scale Plus and Cyclone 5 SoC, the market needs embedded processing in these devices. So I just hope our charter is to build those devices to fill that void and provide these solutions. And again, thanks everybody for your time. This is a great questions again today.
Yeah, that's been excellent. So everybody, thank you very much, and please reach out and contact us as we go forwards.
Yep. Thanks everybody. Have a good day.
Have a good day. Bye-bye.